All right. So my friends got me reading a programming book called The Essentials of Programming Languages. And in it, it's just a book more or less about trying to build programming languages and give you that fundamental knowledge. So we've gotten to the point where I need a parser, as in I need something to take in a string of a program and then parse it so I could have tokens and then mess around with my tokens. And I was curious to see whether or not we have anything in Rust that can do that for us. And it turns out we do. We have something called Pest, the Elegant Parser. So yeah, today I'm going to do a brief intro to Pest. Here we go. All right, so like with anything else, let's first figure out what Pest is. Here's the crates.io page. Let me scroll down a little bit. Pest, the Elegant Parser. Pest is a general-purpose parser written in Rust with a focus on accessibility, correctness, and performance. It uses parsing expression grammars, or PEG, as input, which are similar in spirit to regular expressions, but which offer the enhanced expressivity needed to parse complex languages. All right, so from here we can gather that it is a general-purpose parser that's written in Rust, yay, but also it uses parsing expression grammars. What are those? Well, I'm not an expert in it, but we can go to the Wikipedia page and just get a general idea. In computer science, a parsing expression grammar, PEG, is a type of analytic formal grammar, i.e., it describes a formal language in terms of a set of rules for recognizing strings in the language. All right, so based on that first sentence, we can sort of get the sense that for a PEG to work, we're going to take grammar to describe a set of rules for this formal language, and then we're going to apply those rules to the set of strings that come in as input. One thing that's kind of cool to note is that the formalization was introduced by Brian Ford in 2004. So this is relatively new, and I think online there's also a video of the creator of Python talking about how they switched Python to using one of these as well. So yeah, this is actually used in the wild. Kind of cool. All right. So one of the great things about at least this Crazcalm page or this project in general is the amount of resources it has. So if you come down here, they have a book, which I already have open. I think it's... I just click the link. So one thing to note about the book is that the book is a work in progress. However, the parts that are done do a great job in illustrating that this is a general parser and it can be used for things outside of programming languages. For example, one of the examples is parsing a CSV file. Another one is seemingly an init file. And then they have a parser for JSON, just parsing JSON. And then also, if you search on YouTube, I think there's somebody else that gave a video on how they use this project to parse their log of how many hours they work, things of that nature. So yeah, very powerful tool just for parsing, general parsing. And another thing that's great about this book is it goes over the grammars in detail, giving you all of the like the built-in rules and some examples of how to get a better understanding of using it. So great resources, still a work in progress, but the stuff that is here will get you very, very far. So they have docs. Everybody has docs. But what they also have is an editor, as in you can plug in grammars here, plug in an input, and then mess around with the output just to see, make sure that the list of grammars you have express the things that you want to express or capture the things that you want to express, which we'll take a look at later. But very useful for troubleshooting and just trying to build something from the ground up. All right, so coming further down, we see that they have an example. And the example doesn't really fit too well on my computer screen, so I'm going to have to switch to my terminal because I can capture it more there. But before we do that, we can look at their Pest file. And their Pest file is where they keep all of their grammars. So this is an example of one, right? Where we are defining a few things, I'm going to call them grammars. Alpha, which we're going to say is A through Z, and it can be lowercase or uppercase, right? Digits, which we're going to say is 0 through 9. Okay? And then what we're going to call ident, or short for identifier, I assume, can be a alpha or a digit. And I believe the plus is one or more times, as in repeating. So earlier they mentioned that the syntax is sort of similar to regular expressions. It's not the same, and you shouldn't conflate the two, but there are overlaps. And then down here they have another one, identity list. So I think this one is just to show the example of what an underscore means. And I think the best way for me to describe an underscore, at least from my understanding, is it is a rule that's going to be ignored, as in if the parser sees it, it will acknowledge it, but it's not going to give you it in terms of the output it gives back to you. So silent. All right, so now that we have these grammars, we should try to figure out how to run them. And like I said earlier, well, this is meaningful error, but they have the source code down here, but it doesn't really fit well on the screen. So I'm going to go to my terminal. So give me a sec. All right, so this is the source code. And just like they started out in theirs, well, everything's the same. We have Pest, the crate, that's what we want to use. But we also have Pest derive. Now, one thing I should note is that when you go to the Pest GitHub repo, you notice that they have a lot of nested crates in there. And some of them you use, some of them you won't use. But derive is definitely one that you will be using, and that's exemplified in all of the examples. So coming down to here, we have a parser, and then we derive a parser. And a parser is going to have, I think, a default parse method to it. Now, I'm not exactly sure how everything gets populated, but from my understanding, we have this grammar thing, which points to the Pest file. And the Pest file is the one we already looked at. It was the alpha, digits, identifier, like that stuff, right? Once we point to it, we can use derive to derive, or Pest derive to derive all of the different rules that we need from our grammars and the source code needed to parse everything that we want based on our grammars. So that gets associated to the struct that we put here. And then they auto-magically just give us everything else, which is kind of nice. So if we come down to this part, we have the struct that we created. We have the parse method that we didn't write, but they gave us. And then we have this rule, which has identity list. All right, so rule, I kind of glossed over just a second ago, saying that they created a bunch of rules. These rules, from my understanding, are just a bunch of enums. And identity list, like where did this one come from? Now, if you recall correctly, identity list is here. So more or less, the rules are created. They take the names of whatever grammars you define, and then in your source code, if you want to check or like check against a rule, you use the name that you predefined. So coming back to the terminal, this is going to be our input string, A1, B2. We have an unwrap, and if there's an error, panic. All right, so coming down to the next part. So next we do a for loop over what is returned to us, and we called it pairs. I think they have a formal reason for calling it pairs. I'm not exactly sure why, but that's what they call it. And in pairs, you can see a list of things, and I can print it out in a second so you can see it explicitly. But more or less, you're going to come to a pair, and this is going to be a list of sort of the things that were returned that were parsed. And then you can check to see the rule. You can check to see the span. Span, I think, is like the distance between index-wise, so where it is in the string. And then you can see the text as well that's associated with it. And then if that rule has a nested rule within it, then you can look in those nested rules and then get the information from there as well. So let me run this so you can see the output. So if I run it just now, right, we know that the string was A1, B2. So what we see here is that we have the rule for the first pair, which is going to be an identity. The span, here's the string, A1, It starts at index 0 and it goes to index 2, so like the distance. We have the text. And then in the inner portion, when we go to see what is this identity is made up of, we see that it's made up of a letter, which I believe you can also look at all the other rules for it, and is also made up of a digit. Okay? And then we move on to the second thing that was parsed, which is also an identifier. We see that it is B2. In the span, we see is B2, and we see the indexes of this string. We get the string, and then we look at the inner stuff, and we see B2, or B, as in the letter, and then the digit 2. So just to be clear, I'm going to print out the pair so you can see that as well. Print line. Ooh, I didn't mean to close that. Let me open that again. All right. So coming to the top. So here we are. We're at the top. We're seeing what pairs looks like when it's printed out. And you can see that internally they have a struct called pairs, and everything's put into a pair struct. And this is a list of pairs, which makes sense in terms of the naming convention. But let's continue onward. So we have the rule for the first one, which is identity, which we noted. Information for the span, which was printed out. And then inner. So inside of this pair, we have what it's made up of. So here we see that the inner is also a list of pairs. And we have the alpha, we have the span, so we know where it's from. And then when we come down here, we have the digit and the span of the digit, so we know where it's from. And we note that the alpha and the digit are not built up of anything internally in terms of grammar, so their inners are empty. And we come down to the second item in the list, which was B2, and we see the same information for the most part. Then we come down, we see the alpha. The alpha is a base grammar, so there's nothing inside of it, or it can't be broken down any further. Same thing with the digit. And that's more or less it for this example. All right, so the example is rather short, but one thing I want to highlight is the editor, because that makes all of this much more approachable. And because I'm working through a book, they have an example of a language that I need to try to implement called a let language. Anyway, here we go. This is my attempt to write the grammar for it. All right, so I'm going to walk through the grammar, and I'm go through pretty quickly. So the first one here I have is white space. And I noted this earlier, but it was the underscore, which the parser will note that the pattern exists, but then it will just try to ignore it. And the reason why I have this is because the language that we need to implement for this book, white space is not important. You can have arbitrary amount of white space. And because it's an arbitrary amount of white space, we want to be able to ignore it. And what that ultimately means is that, let me scroll down here and write something. Ultimately, what this means is that things like, and this is a diff expression defined in my grammar, where it's, I think, 3 minus 4. This should be equal to 3 minus 4. Like, those two things, with spaces or without spaces, should be equivalent. So let's scroll back up. So we have number. And here I'm using some of the default rules, which you can find when you start reading through the book. So in the example, they implemented digit, but they didn't have to implement digit because that's implemented for you, and you could just use what they have. So for me, I used what they had, and then I added a plus to it, so 1 or more. And I can show you a number. Let's go with 45. Program, expression, number. and I haven't explained this yet, but more or less, you get to choose the rule that you're trying to work against. So here, it's currently set to a program, and a program has everything in it, right? But if you want to explicitly look at number, then we look here, and this is a number. And if it is not a number, let's say not, it gives me the error messaging. And the error messaging is something that was sort of explained on the crates.io page. We glossed over because, I mean, errors are errors, but they inform you of where the error is located, which is nice. All right, so next part. So another thing we have is an identifier. So the way I wanted to do an identifier, which at least it made sense in my head, is that it can start with a alpha, so a letter, and then we have the squiggly line, which I believe means and then I have another expression here. So after it starts with a letter, it could be a digit or a letter or an underscore, and it could be one or more of those, or zero or more of those. I'm not sure. Let's check. So let's go to identity, and let's put A. I see. So the plus is one or more, but a star should be zero or more, which means now the single A maps to an identity, whereas before it didn't. And I can show that again. So when I had a plus here, it expected an identity, but it didn't receive one because it didn't meet this criteria, as in it needed at least one more digit or letter. However, when I make this a star, we see that now A maps to an identity. And then let me show an arbitrary example of just everything else. So let's say, call it save underscore 32 by. This maps to an identity. And the reason why it maps to identity is because we fulfilled these requirements continuously over and over and over again, right? All right, so another thing we have is sort of the recursive aspect of this. We have a diff expression, which, let me write one out because that's easiest to see. I wrote one out earlier, but 3 minus 4, right? This is the way we define the grammar. We have a negative sign, and then the parentheses, and then expression, and then comma, and then expression, and then parentheses, closing one, and that is a diff expression. And come here, switch it over, and here you can start to see the nesting as well. So we know that this is diff expression, and you know that inside there are expressions, and the expression that we have there is a number, and the expression we have there is a number. So if we wanted to, we could change this to, let's say, save. And now we have an expression that's an identity. So we covered numbers and identities, but we haven't covered what an expression is. And this is where we're going to do next. So here I have an expression, and I defined it as let expression, if expression, zero expression. Those are just some other stuff here we haven't covered. But more importantly, there's a number and there's an identity. Now, if you notice in the diff expression, there's an expression. But within expression, diff expression is here too. So this is sort of like a weird recursive thing, but everything works out pretty well, which is kind of nice. So I have some other methods here as well, like zero expression, if expression, let expression. They're more or less examples of how to do the same thing. One thing to note is that order matters in terms of how things get matched against. So for example, how did I break this before? If I put let expression, which let me give you an example of a let expression. Let save equal 42. I'm going to a program because a program is expression, and that's just everything. Oh, yeah, I didn't finish writing it. Save in, and then another expression. And then if I move this to the end, X. All right, so just a second ago, we had a let expression down here, right? But now, because let expression was moved to the end of the expression list, this got matched to something else first. And it got matched to identity because, technically speaking, the letters let map to an identity. So does save. The white space is ignored, so all of them just identity. And then afterwards, we have something that it doesn't really understand. The equal 42, blah, 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 blah. And that is just not being captured here. So in a sense, you can like get a gauge of how the ordering of your expressions matter, and they're being evaluated from left to right. So let me move this back over. And bam, we now have everything we wanted here. All right, so yeah, that was pretty much everything I wanted to cover. Just a brief introduction to what Pest is. And I just want to give a quick shout out to the people who created it, because thank you. As long as I'm going through this book, I'm going to be heavily dependent on your repo, your project. And if you like the project, please check it out. It's actually really, really cool. Outside of that, we've reached the end of the video. If you like the video, hit like, subscribe, yada, yada, yada. Till next time, peace.